All right, welcome to Chapter 2, Biomechanical Principles of Motion. Throughout you'll see a whole heap of different words here, and by the end of this chapter you should be able to understand and be able to explain all of these concepts. You need to take notice of the key knowledge and then therefore the key skills because they're relevant to your assessment. So make sure you take the time to have a look through and read this. Also, what I've put in here is just a breakdown of that and what we'll be covering in this chapter. When we look at biomechanics, we're looking at biomechanics in terms of that it is the study of the mechanical principles that govern human movement, okay, and we can use that to help develop and refine movement through analysis. When we talk about kinetics, we're talking about the study of force that causes motion. Okay, so force causes changes in motion, and we cannot get a change in motion without a force. Okay, so this is a branch within biomechanics. When we look at kinematics, that is the description of motion, so how we would describe it. Okay, so it gives a reference to time, distance, displacement, and velocity, which will all be covered later on. Throughout this chapter, you'll find there's quite a few videos. It's highly suggested that you watch these to help consolidate your knowledge. One of the first parts we look at is motion, okay, which is movement. So it's a change in position of a body in relation to time. Okay, so it involves a complex combination of different body parts, and the main two that we focus on are linear and angular motion. We have this thing called general motion, which is essentially the combination of both of those. And most movements is a combination of both linear and angular. When we look at angular motion, it is motion that occurs either in a straight line or a curved path. If it's a straight line, it's called rectilinear. If it's a curved path, it is curvilinear. And it is commonly referred to as translation. Now, true linear motion is very rare, okay? The rare exception will probably be, as we can see in this picture, a downhill skier that is going in the same line, in the same motion. So there is no element of rotation at all. So it's very rare that this occurs. And there's a video on this to help demonstrate that. When we look at angular motion, that takes place when a body moves along a circular path. So that's what we would commonly refer to as rotation. This will occur when the body moves at the same angle, in the same direction, at the same time, and it's usually around some type of axis. So it could be either an internal axis, such as internal of the body, or an external axis. So if we're looking at, it might be a ball and then there's some sort of axis on it. The other example we can look at here is when we're looking at the high bar, so the axis is going to be the actual bar for which the gymnast will rotate around. Throughout this chapter, you're going to have to understand the concepts of mass, inertia, force, momentum, impulse, and then later on we look at Newton's 3 laws of motion. So these are important to be able to understand and therefore apply. When we're looking at mass, we're looking at the quantity of matter found within a body. So when we're talking about mass, we're measuring it in kilograms. So, for example, you might be 70 kilograms on Earth. Okay, that is your mass. But when you go to space, your weight is going to be less. So your mass still stays at 70 kilograms, but you weigh less in space. I hope that doesn't confuse anyone, but you should just refer to it as mass. Now, if we have a person with a large mass, they're going to be composed of large quantities of matter. And therefore, a person with small mass is going to have small quantities of matter. That last dot point about there being a direct relationship between the amount of mass and inertia, we're going to discuss that a little bit later. When we look at inertia, so that is the resistance of a body to change in its state of motion. Okay, so that is, if we have an item such as our rock sitting on the ground, it is what we would describe at rest, okay, and it is reluctant to move. Okay, so it's a resisting change. So that's what we would call static inertia. Okay, so it's the reluctance of a heavy piece of sports equipment to move from the ground. So that rock down there is going to be very difficult to move. Okay, dynamic inertia the example we can use is a rugby player. So they might be running with the ball. Okay, they're going to be reluctant to be able to change direction or velocity. Okay, so it's a lot more difficult to knock a rugby player off them running in a straight line. You can use both these examples to help demonstrate that. For example, the static inertia, where the person in the gym is trying to deadlift that item, so they've got that weight is resistant move, so therefore that person must provide a force which is going to overcome that inertia, and we'll discuss that. So the relationship between mass and inertia, so there's a direct relationship, meaning if we have a small ball, for example our little golf ball here, that means it's going to have less inertia, okay, which means it's going to be easier to move. So you should be able to understand that if you just roll either a table tennis ball or a golf ball, it's pretty easy to move. It's also pretty easy to stop. If you have a larger ball, for example, might be a Swiss ball, or you can see these oversized ones, which have got people inside, they're going to have a lot more inertia. So they're going to be a lot more reluctant to stop moving, which means they're going to be more difficult to be able to slow down or stop. You would think about how would you be able to stop this ball from going down the hill. It's going to be very hard compared to our golf ball. When we look at force, so force is the product of mass and acceleration, which is F equals ma. You're really going to need to know this. Now, it is measured in newtons or an N, okay? And this relates to, objects are either in a state of rest, meaning that you're not moving, or in a state of motion, okay, where they are moving. To be able to change that, a force must be applied. And a force can cause an object to accelerate, decelerate, or change directions. So the different types of forces that you might have, you might push something, you might pull something, it might be a straight line force, it might be a rotational force, it might be contact, for example, it might be getting tackled, or it might be a field force. And some examples down there, we've got gravity, okay, which is an external force. We've got air resistance, okay? For example, if you're throwing something through the air. We've got buoyancy, so that is a force in itself, and we're looking in terms of water. And an internal force is the contraction of skeletal muscles, okay, to be able to generate force. When we look at momentum, that is the product of mass and velocity. So momentum, we write it as P, so P equals mv. Now, velocity is, so mass versus velocity. Velocity is measured in meters traveled per second, and we look at that a little bit later on. But essentially, if an object has zero velocity, then it has zero momentum, okay? The greater the mass, which will mean the greater the velocity and the greater the momentum, okay? So if you think about something that is heavy, okay, it's going to have greater momentum. So if we look at this table here, it's a comparison of a 100-meter sprint, all right? In these situations, we have two athletes that are 80 kilograms and two athletes that are 90 kilograms. So we're looking at their peak velocity, okay? So in a way, it's essentially similar to their peak speed or acceleration, okay? Athlete 1, all right, is 10 meters per second. So if we times 80 by 10, because that's our formula here, it is 800, okay? When we're looking at momentum, next one who has peak velocity is 9 is 720. We find that the person which has the greatest momentum is the athlete which has the heavier mass and the higher peak velocity, so 900. Now, when we're looking at the conservation of momentum, okay, if we use this example that we have on here, and you can watch that video, for example, of you using a bowling ball to hit some pins. So when the two collide, so the bowling ball collides with the bowling pin, okay, that momentum is conserved, so it stays the same, okay. What happens is that the force from the bowling ball is therefore applied to the bowling pins. That will cause the bowling ball to slow down and decrease its velocity, and that will cause the bowling pin's velocity to increase. Remember, the velocity or it's zero momentum currently in the bowling pins because they're not moving. Okay, what they move because of the conservation of momentum, so it is transferred across. The same can be said about a golf ball. All right, when the golf club comes through in contact, the ball currently has zero momentum. The conservation happens, the force is applied, the ball will increase its velocity, and the velocity of the golf club will decrease. But if you combine them, it is staying the same. When we look at force summation, this is essentially saying that to help us get the maximum amount of force or generate the most amount of force, we need to have the correct timing and sequencing of body segments and muscles throughout this range of motion. Okay, so if we want to get maximal force production, for example, when we're looking at our shot putter here, we want to make sure that we get the correct timing of our body segments. It is no point trying to use our shoulder and our hand or elbow before we use our legs. Okay, so controlling the quantity of force generation is often important. Because if we look at our golfer here, they do not want to generate maximum force when they are putting on a golfing green. Okay, they need to actually modify that to not overhit the ball or not generate as much force. When we're looking at simultaneous force summation, that's essentially saying that we need to use multiple body parts at the same time to produce force. So if we think about a sprinter at the beginning of a long race or a long jumper or a high jumper in the run-up, okay, when they take off, they're going to have multiple body parts moving at the same time trying to generate the force. So an athlete will try and take off using their legs, but they'll also have their arms which will rotate, okay, and then that will help generate that force. So we need to understand that as an example of simultaneous force summation. Another version of that is sequential force summation. That is the activation of body parts that are used in a sequence to produce force. Okay, now this is the most common form in sport, and it's more successful and will produce a maximal amount of force if we use these below principles, which we're going to go through. But you essentially should understand that we use 1, 2, 3, 4, 5. So we're going to use different body parts from 1 all the way up to the end, and then the last part is the final part of the movement. So if we're looking at this here, the first one of those dot points was activating the stronger and larger muscles first. So if we want to try and generate the most amount of force, we need to activate large muscles. Most of those large muscles are going to be in the lower part of our body. So more often than not, it's going to be our lower legs, such as our quadriceps and hamstrings and glutes. So this force that we generate, okay, can then be passed on to other parts of the body, such as the core, such as the upper body and the shoulder. So our larger body parts will have a higher mass, okay, but that means they'll have lower acceleration. But if we transfer this momentum so that we generate, it will transfer into smaller body parts which weigh less, so in terms of their mass, but they can accelerate faster. So if we're looking at a discus thrower, for example, they will use the lower legs, generate the force, it will transfer up when they rotate, and then it'll come through their shoulder, and then the final part will be out their hands. Another example we have here is using as many body parts as possible, enabling force to be generated over a greater period of time. So if we think about this, if we're using more body parts, it's going to mean that we're going to be able to apply a force which will create greater momentum. So if you recruit more body parts in a sequence, then it increases the total time where momentum is generated. So if we compare an athlete using crouch start, they have less body parts on the ground. There is less of their knee that is going to be flexed. What that'll mean is that they can probably take off a little bit quicker. All right, so they'll take off faster, but they won't have as much momentum. If you compare it to an athlete that uses blocks, so what that means is that there's a lot more flexion in their knees, so they're a lot more hunched, okay, whilst they will not take off as quick because there's a lot more force that has to be generated through that knee joint to get them to start off, it'll mean that there's a greater time for that, so that means there'll be more momentum generated, and that means that they'll be able to apply that force over a longer period of time. Our next one is transferring momentum from one body part to another when at maximum velocity. What this means is when we are performing, a skill in a sequence, we must make sure that we use the sequence in the correct order at the correct time. So if your movement happens too early, okay, it might be before your maximum momentum, so you might not get the most out of it. If it's too late, your momentum might drop. So this can be the same if we're releasing or striking a projectile. The example I have used here, okay, is in a bowling run-up. So you want to make sure when you are running in that you are releasing it at the correct time. If you let something go too early, you might not be able to generate as much force, or if it's too late, your momentum might have dropped. So that is making sure that we have a sequence. Okay, everything that happens occurs in the sequence and it's transferred from one to another at the correct time or maximum velocity. The presence of a stable base for maximal acceleration of body parts to occur so that momentum can be transferred successfully from one part to another. So if we think about it, think about our baseballer here, they need to have a stable base for them to generate the acceleration. So a golfer, or we can use the exact same thing for a baseball player, you need to have a strong trunk and torso to be able to sequence and time the transfer of momentum to from one body part to another. And this slow motion video, you can see the generation of force when they are stable, and then the bat is allowed to come through. We move on to angular momentum. That is the product of moment of inertia and angular velocity. So angular momentum is expressed as h, we have moment of inertia is I, and then we've got a nice little W looking symbol of angular velocity. So moment of inertia is a measure of an object's resistance to change in its rate of rotation. So we think about inertia, we're talking about the resistance to move, resistance to change. This is what we're talking about. Moment of inertia is when we're looking at it from an angular perspective. So this is based upon Newton's first law of motion, which is that an object will stay at rest or continue to travel in the same direction at a constant velocity unless acted on by an unbalanced force. So this is obviously going to be dependent on the mass of the rotating object or body and the distance the weight is distributed from the axis of rotation. If we think about these two examples here, think about which one is going to be easier to swing. If you think about which one is going to be easier to swing, it's going to be this one here, because the mass is closer to the axis, which is where our hands are, okay? So there is less weight at the end, all right? It means that there is less moment of inertia, so there's less resistance to change, okay? And there is less angular momentum. So they will be able to move that a lot faster. On the left side here, all right, the lighter part of the weight is near the axis, so the heavier part is further away. So that means that there'll be a greater moment of inertia because it is distributed away from the axis, which means there will be a greater angular velocity, all right, meaning that it will take a little bit longer to hit the ball. Now, we need to think about that. A baseballer needs to be able to react to the ball coming towards them, so a pitcher throwing it at them. They want to make sure that they, one, are able to react to it, but two, still able to increase their angular velocity and momentum. So that's where the trade-off comes between having a too heavy bat, which will generate more momentum, but it will reduce the reaction time. So that's why you see variations in the weights of bats that people use in different striking events. Now, you can alter an object's moment of inertia by altering how a striking implement is held. If you hold a bat lower, it'll decrease the center of the bat's mass and the axis of rotation. So if we use our little example here, you can see that our little cricketer is holding the bat a lot further down. This is commonly referred to as choking the grip, and it's in both examples. Okay, that gives them greater control, and it decreases the center of mass. So it feels like it weighs less, and there's less rotation. All right. So you should see that in younger kids. If they're using something that is too big for them, they have to hold it further down to be able to control it. So that will decrease the moment of inertia. You can also see this when you watch this video of a diver. So they will decrease the moment of inertia by tucking their body in. There'll be a greater moment of inertia if they're obviously, further out when they're completing, so they're not in a tuck position. We then look at Newton's laws of motion. So you'll need to know these, and my suggestion would be know them word for word. Okay, so that is that a body continues, for Newton's first law, a body continues in its state of rest or uniform motion unless a balanced force acts upon it. So our example is that these balls here, for example, you might have seen one of these. They're on a piece of string. They won't move unless you swing one of them back and it'll hit on it, and it will continue. Newton's second law says that the acceleration of an object is directly proportional to the force causing it, is in the same direction as the force, and is proportional to the mass of the object. Essentially, force equals mass times acceleration. So the greater the force, which will mean the greater the acceleration. And Newton's third law is that for every reaction, there is an equal and opposite reaction. So if we use the example of the skateboard, the force and the pushing forward that we have here down and on this skateboard will cause the opposite reaction. So it's the same thing, is that if we're pushing against a wall, all right, the wall shouldn't move because there's an equal and opposite reaction coming against it. And this video gives a good couple of examples of that in sport. And there are some other ones that you can find. Next part we look at is impulse. Okay, so impulse is force times time. So the greater the impulse we have, the greater the momentum that we generate. So for greater impulse to occur, force should be applied over the greater period of time. So the way that we look at this here is that we're looking at a tennis player using a racket with loose strings compared to tight strings. The tighter the strings will mean that there is less time that the ball is in contact with the racket. Okay? The looser strings mean that there is more time in contact, resulting in a greater impulse and subsequent momentum. So that's where we're looking at is greater momentum, but there's obviously not as much power in that. And the same thing when we're looking up here. So we can use impulse to absorb force over a longer period of time to reduce impact. So if we're looking at cricket pads, we're obviously trying to reduce the impact so that when the ball strikes it, okay, it absorbs that force. Same as a high jump mat when a person lands on that. You can also talk about the fact that if a person takes a catch, if they absorb that over a longer distance, then it's obviously going to be a lot more beneficial. So if they rotate with it. On this first half, we compare on this top part, the standing throw and the 1.5 turn throw. So we'll look at the two different techniques. With a standing throw, you use that little half spin, meaning that the force is applied over a smaller period of time, so it has a smaller impulse. If we use the 1.5 turn, we're going to generate greater impulse and greater momentum, okay, because the momentum is happening over a longer period of time. So that's obviously going to increase the distance that we can throw. Next thing we look at are linear and angular different concepts. So you'll need to understand the difference between both of them and make sure you don't confuse them in terms of make sure they're linear and angular. So when we look at distance, that's the path traveled from start to finish regardless of direction. Okay, so if I run 100 meters, the distance is 100 meters. Okay, if I run up 5 meters, touch a wall and come back, then the distance is 10 meters. Displacement, though, is the difference between an initial position and the final position of an object. And if we look at it here, we can discuss it. So if we're looking at, a 50-meter swim, if we swim from one end of a 50-meter pool to the other, the distance traveled is 50 meters. So in terms of displacement, we're talking about the distance from final position to initial position, it's 50 meters. But if we swim 100 meters, so we swim up one end 50 meters and then come back to the starting position, our distance covered is 100 meters, but our total displacement is 0 because we are back where we started. And this is another example here. So we have a 50-meter pool. Okay, our swimmer swims up to the end, so the displacement is 50 meters. But if they swim up and then back, so to halfway, it is 25 meters because it is from the finishing position and the starting position, and that's 25 meters. Our distance in this example would be 25, 50, 75 meters. When we look at angular distance and displacement, so angular motion, when we're looking at this, it is when a body rotates from one position to another. All right, so you got to think of its rotation. So the distance is the total of all angular changes that result from an object or body part angle between start and finishing position. So if we think about if someone does a 360-degree turn, the distance is 360 degrees. The same as displacement is the difference in degrees between an object's or body part's initial and final positions. So it's measured by the smaller of the two angles. And it usually has a size and direction. It's usually measured in degrees and radians, but we will use degrees for this example. So when we look at this here, the angular displacement of 10 pin bowlers between these two positions, so our start position and our finishing position, okay, is 120 degrees. Whilst they've moved their arm back and then come all the way through, so their distance is 240 degrees. Remember, 360 degrees is the whole way around. We have to look at the smaller distance between the two. That is our displacement. So if it's 240 degrees in terms of distance, then the displacement is going to be 360 degrees minus 240, which gives us 120. And that is measured in degrees. When we look at linear speed and velocity, okay, speed is the rate of motion. So that is, we usually measure that as S equals distance over time. Okay, and distance is usually measured in meters. When we look at displacement, that is, velocity, that is displacement over time, okay? So speed, we're looking at distance, velocity, we're looking at displacement, and it's measured in meters per second. So if we look at this example of swimming from one end of the pool to another, where our distance was 50, our displacement was 50, and it took 25 seconds, to swim. If we're looking at our average speed, so speed is distance over time. So 50 divided by 25 is 2 meters per second. And we need to make sure we have it obviously in the correct units. The average velocity, again, is displacement over time. Our displacement was 50 meters, so it ends. Our average velocity was 2 meters per second as well. If we use our example of the 100 meters, so we swim up from one end back to another, so we swam 100 meters and it took us 50 seconds, our average speed is going to be 2 meters per second because 100 divided by 50 is 2 meters per second. Our average velocity is going to be 0 because our displacement is 0, because in the 100 meters we swam from one end to another and back. So our displacement is 0 because our starting position is the same as our finishing position. So when we're looking at angular speed and velocity, okay, angular speed is the angular distance covered by time taken. So distance, usually in degrees, over time. So it is very similar. You just need to think about it. The angular is more going to be in degrees, whereas linear is going to be measured usually in meters, okay? So, and our velocity is dividing angular displacement by the time taken. So our angular velocity is the initial angle minus the final angle, okay, over time, and that's measured in degrees per second. Linear acceleration, so that is the rate of change of velocity over time. So our velocity, which will be our final velocity, minus our initial velocity over the time. So we can work out if we are accelerating and whether that be a positive acceleration or a negative acceleration, which we usually call deceleration. And it's measured in meters per second squared. If we have an acceleration of 0, that doesn't mean that we've stopped. It just means that we're not speeding up or we're not slowing down, and we usually refer to that as a constant velocity. Throughout acceleration, we also need to understand that we'll have downward forces caused by gravity, and that's usually 9.81 meters per second squared, and that will impact on an object's acceleration. The example we can use here is a 100-meter sprint. Okay, when we start off the race, our acceleration, we're going to have maximum acceleration. We're going to try and accelerate as fast as we can so that we can increase our velocity as fast as we can. Our distance is the same, so we're running 100 meters. When we get to around 4 to 6 seconds, what we find is that, and as we get towards 6 and 7 seconds, we'll start to have negative acceleration because you cannot go any faster. So we actually do not accelerate, we just remain at a constant velocity, and you can see that there, it's about the same. And then what happens towards an end of a 100-meter race, you actually start to slow down or decelerate, okay, in that final part, and we can see that matches up here with our velocity as well. So we actually get slower. So we need to be able to understand a graph like this. We will accelerate, we'll continue to accelerate, and then we will have a period of constant velocity, and then we will decelerate. Angular acceleration, that is the rate of change of angular velocity over time. Okay, so it's the same. We're just looking at the change in velocity in terms of an angular perspective. So if we're looking at a gymnast and they rotate around a high bar, so that was that bar that we saw previously, and they speed up from 100 degrees per second to 300 degrees per second in 0.5 seconds, they'll have an angular acceleration, so they'll be speeding up, of 400 degrees per second. And you can use this formula here. So we use our final velocity, which is in blue, minus our initial velocity, which is in pink, over the time it took, okay, and that's what we get. It's measured in degrees per second squared. We then go to projectile motion. So that's going to be a projectile is an object or body that is released into the air. Now that's usually going to be impacted by usually two external forces, one being gravity and the other one is air resistance. Air resistance is a force that's going to work against motion. So if we think about it, more often than not, we usually have air resistance when we're throwing a projectile in the air. And we'll also have drag forces which will slow it down and reduce its flight time. So try and pull it back to Earth. With the projectile motion, there are going to be different factors which are going to impact on that. So the higher the velocity, the greater the air resistance. If you have a lower mass, then there's going to be a greater air resistance as well. The shape is also important because a streamline, for example, a cyclist wearing a helmet like this, they're going to experience less air resistance, okay? So what that means is more air is going to flow past this helmet and over the back of a cyclist, meaning that there's less drag. So if you think about if you ride a bike and you have your arms out, okay, compared to if your arms are tucked in. If your arms are out, then you're going to have greater air resistance. Whereas if your arms are tucked in, there is less air resistance. If we look at, and so that also refers to the surface area. So the greater the surface area, the greater the air resistance. So if we look at our shuttlecock here from badminton, they've got little holes inside, so that reduces the surface area. And the nature of the surface area. So a smooth surface area will decrease drag, and then there's less air resistance. Okay, so you think of something that is smooth compared to rough, all right? If something is smooth, there's going to be less air resistance. When we're looking at gravity, obviously gravity acts against the motion by pulling an object back towards the ground. So that's what we would call a vertical force, okay, on a projectile. Some different things we need to look at as well, and which can impact on the projectile, so how we release projectile, is the speed of release. So the force applied to a projectile will have a large impact on its motion. If we can generate more force when we go to throw, that means there's going to be a greater speed, which means we're going to have greater distance. Okay? How we achieve this is usually through working on our technique to increase the force so that we use more body parts. And if you think about a baseball thrower, if they stand still and throw compared to a run-up and throw, they're obviously going to be able to throw more with the run-up because you're going to be able to generate greater force, which means there's going to be a greater speed of release. When we look at angle of release, okay, we need to make sure when we're releasing a projectile that we need to understand is that there's an optimal angle of release. Okay, this optimal angle will reduce the impacts of gravity and air resistance, and it's usually about 45 degrees. However, most sports will probably have an angle of release of either higher or lower. So, for example, if we're hitting a forehand in tennis, our angle of release is going to be probably lower than 45 degrees, because if you think about it, a tennis player wants to hit it as close as possible to the net, so just over the net. The higher they hit it over the net, the easier it is for the person to return that shot. When we look at a dig in volleyball, we're going to have a higher release than 45 degrees because we want the dig to hit the ball up so that our teammate has a little bit more time to be able to respond to that shot. And you can see here there are different examples. So if we're doing a layup, obviously it's going to have a higher angle release. A badminton serve is about 60 degrees. If we think about javelin, it's about 30 degrees, okay? And there are some other examples there. And you can use the example of lawn bowls, which is obviously 0. When we look at how you can alter the angle of release in the following sports, if we think about golf, you can do that through the different type of golf club that you use. So the different types of wedges or irons, okay, will have a different angle, meaning that that will impact on that angle of release of where the ball strikes, okay, and that will impact on the amount of spin that is created on the ball and therefore the distance. In football, that could be how low you release the ball towards your foot. If you have a higher release towards your foot, that means it's going to impact on that angle, okay, and impact on that ability to be more precise. We look at height of release. If you compare 3 different people, all right, and their angle and speed of release are the same. So if you release these three different balls and they have the same angle and speed of release, so they all release from the same, then an object released from a higher point will travel further. Okay, so that is why sometimes if we're using the exact same speed and we have a taller person, they'll be able to throw it further. We go through now levers. Okay, a lever is a rigid structure that rotates around an axis. Okay, so we use levers to improve performance, and we usually use equipment in addition to body parts, and that will allow us to generate more force or speed more easily. And you can think about examples such as using a crowbar, a wheelbarrow, or scissors. They're examples of using levers. The most common components of levers we have is the axis, which is our turning point. So, for example, if we use our tennis player here, that is their hips. The force of where, so the point where the force is applied. So, for example, using this tennis racket, where the force is coming from our shoulder, and the resistance. Okay, so whatever a person is trying to move, so that's going against the ball there. Okay. There are 3 different types, so and it depends on the location of the axis, the force, and the resistance. So we'll go through each of those now. First class lever, if we think about a seesaw, so a force is coming up. If you push down on the ground, okay, on the seesaw, the load at the other end will go down. So what we need to understand is force. Fulcrum is also our axis, and load is our resistance. In this example, the axis is in the middle and the force and resistance are at opposing ends. Now, there are limited examples within the human body. Our head and our neck is an example of that, and we can see that here. Our second class lever, if we think about a wheelbarrow, so we have our axis at one end, okay, we have our resistance in the middle, and then we have our force lifting up at the other end. Okay, so we're thinking about a wheelbarrow. Our example in the human body is if we lay our feet or we're standing upright and then we push onto the balls of our feet, okay, that's our axis here. We have our resistance pulling us down and our force is generated through our calves or our gastrocnemius. A third class lever, example of that is usually striking a ball or an object, or it can be a fishing rod. So where our force is in the middle, okay, and our resistance and our axis are at opposing ends. And that's usually common within the human body, okay? So we're thinking about it, we're using a force, okay, that is pulling up, for example. So we have our bicep on the, and the tendon attaches over the top onto the radius and ulna. Okay, the force is coming up. The resistance, if we're holding onto, for example, a weight, okay, is pushing down. Okay, we've got gravity there, and our axis could be the example of our elbow here. There are plenty of different other examples you could see throughout the human body. When we use these, so what we're trying to use levers for a mechanical advantage. Okay, so if we are trying to be able to, for example, lift up a heavy object, we're going to use a lever for a mechanical advantage. How much of that advantage we get is dependent on the type of lever we use, the length of the force arm, and the length of the resistance arm. So if we're looking at the force arm, that's the distance between the axis and the force. Same as the resistance is the distance between the axis and the resistance. Okay? To look at that advantage, we go force arm divided by resistance arm. So if our force arm, so the force we have, is longer than the resistance arm, then the mechanical advantage is deemed to be greater than 1. That means that the force that is needed to move the load is less than the force of the resistance, meaning, essentially, that less effort is required to move the resistance. If it is more, so the greater resistance, that means we have to try and generate more force. Okay? We now move on to equilibrium, which is a state in which there is a balance of forces or influences in opposition to each other. When we look at static equilibrium, that's when all parts of the body are at rest. So if we think about a ball stationary on a tee, or we might think about our gymnast here that is stationary. Okay, so we're thinking that there's no movement here. All right, so there is zero velocity and zero acceleration. Okay. When all the body parts are moving, so for example during a floor routine, with the same constant velocity created by balanced forces, this is when we're looking at dynamic equilibrium. We move on to balance. So that's the ability to control the state of equilibrium. So if we think about static balance, which is one of our types, that is a person being in control of their position while they're stationary. So we think about a sumo wrestler, they're static balance, they're standing still, okay, they're able to hold their position. Dynamic balance is when a person is in control of their position while they are moving. So if you think about an ice hockey player controlling the movement with speed and control, it might be a basketball player while they're running and jumping, it might be a netball player as well. When we look at stability, okay, we're looking at the degree to which a body resists changing its equilibrium, okay? And there are a few different factors that will impact on that, okay? And we'll go through them. So when we look at it, we look at center of gravity. So we're looking at a central point of an object about which all of its weight is evenly distributed and balanced. And that shifts in every movement. So when you look at this picture here, it's important to understand the red dot is center of gravity. So when a person is leaning forward, their center of gravity is through the middle of their hips. When they're in a push-up, it might be slightly higher up when you're standing up as well. So you need to understand that based upon our movement, it's going to change our center of gravity. What you also need to understand is we have a line of gravity, okay? So that goes, it's an imaginary line that essentially goes through our center of gravity, okay, through to the base of the support, which is actually the area of an object that is in contact with the surface. So we're standing upright on the ground. Our base of support is the ground. Our center of gravity is usually just above our belly button, and the line of gravity is smack bang straight imaginary through the middle of us. However, if we lean forward, okay, our line of gravity is through the center of gravity. The center of gravity actually moves a bit further forward. Okay, so it's not directly through where the basis of support is. That's why we'll be considered more unstable. Okay, now the further that the line of gravity is from the base of support, so for example in our person here, then there's going to be a lot more instability and a lot more rotation. And you should think about it, if you lean further forward, you're going to be a lot more unbalanced than if you're standing upright. To increase our stability and balance, there are a whole heap of different ways that we can do this here. For example, if we go a little bit lower, so we're going to lower our center of gravity, if we use the example of our sumo wrestler here, and if we try and ensure the line of gravity is over the base of support, that's another way. We also might widen our stance, which is going to increase the size of the basis of the support. An example of this might be if you're standing on a train, if you're standing upright and the train's moving, to stop yourself from falling over, you can either widen your feet or slightly turn side on as well, and that will help improve all these areas. If we're going to have more stability, obviously we're going to, if we increase the mass, that's going to help, okay? As well as extending the base of support in the direction for which a force is coming. Now, this isn't always beneficial. If we think about sports such as sprinting and batting, you want to actually be able to move quickly. So the more stable you are, the harder you are to shift. So in these examples here, we've got our example of our cricketer. If their stance is too wide, yes, they will be more stable, but they're not going to be able to react as quickly or move as quickly. So there actually needs to be a trade-off between being in a stable position and being in an unstable position, but it's more controlled for quick movement. So with a cricketer, they'll usually reduce their base of support and raise their center of gravity, okay? And then they'll move their line of gravity closer to being outside, so they'll move it a little bit further forward so that they can move more quickly. Ways to reduce stability, so that in that way it's going to promote agility, is usually raising an object's center of gravity, and it also might be narrowing the base of support. If we use our tennis players here, a tennis player in red is going to be a lot more stable because they've got a wider base of support in comparison to our player up on the left, which has got a narrower base of support, so they're going to be more agile. We then look at eccentric forces, okay? So if we want to promote angular motion, so movement of an angular kind, it's got to be produced by a force, okay, that does not act through the body's center of gravity. This is called an eccentric force and will result in an object rotating, and then we usually call that spin. And you can look at these two examples here to understand how rotational spin occurs. The rotation is caused by torque, okay, and that's referred to as the moment of force. That's going to be dependent upon how much a force is applied, so the size of the force, and the length of the lever arm, so the distance that the force is applied away from the axis of rotation. So if two equal eccentric forces are applied in two opposing directions, the object will rotate without moving. So if we look here, we've got rotation here. So when we have our eccentric force from one end, it will cause us to rotate around a center of gravity. Now, hopefully this has been able to help you go through biomechanical principles. You need to make sure that you complete all chapter questions, our review questions and our exam questions, and it's going to make it a lot easier for you to understand when you get to Unit 3 out.